Well, it's my pleasure to introduce Jasmin for her third talk on the dynamics of polynomial. Please, you can start. And students, you can make questions, okay?
Yeah, you can, actually, I have a question to answer too. Yeah. Okay, let me share my screen. Do you see my screen? So it's all white for the moment.
Yes, yes. Very clear so far, very clear.
Very clear, right?
So far, yeah.
So to answer the question, actually, I didn't motivate at all why we are interested in finding a polynomial endomorphism of C2 with a wandering domain. So I didn't do it, and I will do it later. So, but this is related to the question. So let me go to this question, and then I will go back. So let me change a little my plan for today. It's fine. At the very end, it will all patch up together. Okay. So the question that one has in mind. So let me go back to lecture 1 for 1 sec. Yes, it's here. Oh, I'm not so good. I didn't do it on purpose. So remember that in dimension 1, you have Sullivan's result. Sullivan's result is telling to you that, look, if you get pick a polynomial NC, you will not have a wandering domain. Pick a rational map of degree at least 2 NC hat. So in P1 of C, in the compact case, you will not have a wandering domain. So of course, you can ask yourself, what happens? So in here, the Riemann sphere, what I know, it is that it is compact. So what happens if I drop this hypothesis? And actually, if you drop the hypothesis of being compact, so you take an entire map of C, so it's no more a polynomial, then you can have wandering domains. So let's go back to today. Yep. So in here, well, let me make a remark. Actually, I think the first example goes back to Baker. I didn't write down an example in here, and since this is from one dimension, I'm not so comfortable with that, but I could find it back for tomorrow if you want. So there exists actually plenty of entire maps functions with wandering domains. And so now whenever you go in dimension, well, let's say that we're not too brave and we just go to dimension 2, which is still a lot. So we go to dimension 2 and you ask, what about wandering domains? So having for 2 components with an infinite orbit, so wandering domains here. And say CK, or well, sorry, I said in dimension 2. I don't know why I want to go to dimension K. Or P2 of C. And well, the first thing that you have in mind is that since you add wandering domains in dimension 1, you should be able to find them in higher dimension. So of course there is always this, well, I was going to say stupid, but it's not stupid. The reassuring thing of saying, look, I take a 2-dimensional map, which is not exactly 2-dimensional map because it's 1-dimensional in one coordinate and 1-dimensional in the other coordinate. Then if you take a direct product in C2, so direct product in C2, f of z, g of w, well, this is fine, okay? If you find wandering for 2 component in here, then you take here a polynomial, well, you know, you're going to be able to construct a wandering domain in C2. But now you said, oh, but who are the real complex analog of holomorphic entire functions? And what you're going to ask yourself is, can I find an automorphism of C2? So something which is a little more rigid, which is still holomorphic with a wandering domain. So say, does it exist a biholomorphism of C2 with a wandering domain. And the answer is yes. And this is due to Fornes and Sibony. And okay, they're not here, they will not kill me. I think it's 1998, but I'm not sure. But well, you can find it back. I can give you those references. I didn't prepare that. So, but this is something which is true. It is, one can prove it. And what is the problem in this example? Well, there is no problem. It's a good example, but it doesn't. So it does answer to this question in C2, but it does not answer in P2 of C. So you somehow expect that in dimension, so since in dimension 1, whenever you drop compactness, you get wandering domains. So somehow, well, it is reassuring to say that, well, this is true also if I go in higher dimension. What it is more difficult is what happens to the compact case. So, and the compact case is the case of P2 of C. And of course, I can again ask, can I use products? But direct products cannot give me a wandering domain in P2 because, well, actually, you can also ask me, why am I so stubborn and working in C2? Because in P2, you usually have 3 coordinates, right? But if I have 2 polynomials in C, in C2, then I can homogenize, add a third variable. And if I add this, since in here I have a direct product, I have no problem in doing that, I will be able to build a holomorphic endomorphism of P2 of C. Okay? So what I was saying is, if I take 2 polynomials with separate variables, I will not be able to get where I want to get, meaning to see a wandering domain if there is any. Because, well, in dimension 1, I know by Sullivan's result that I don't have a wandering domain for a polynomial. So I can't go there. And even if I had a Blaschke product, even if I'm not such an expert on this stuff, but they don't have, am I correct? I think they don't have a, yeah, I think so, wandering domains. And so I can't use something like that. So what the idea was, and the idea is not our idea, it's an idea of Lubitsch. So let me put it here. So idea by Lubitsch. I mean, I don't know how many ideas go back to Lubitsch, but this was a wonderful one, like a lot of them. So in here, what he said is that, look, maybe we are asking too much. Maybe taking a direct product is not a good idea. So use Skew Product. So a Skew Product is a map. So we are in dimension 2 of the form f of zw. So in here it's 2-dimensional, no problem. And in the second coordinate, I take a map which is 1-dimensional. So in here, and actually I will add polynomial ones. So f and g are 2 polynomial maps. So g is 1-dimensional. So I know exactly who are the 2 components for g. And well, I will use the structure of this Skew product in order to be able to prove, well, to see whether or not there is a wandering domain. And we are always considering polynomial because we want to get back to P2 of C. So we are building a 2 component in C2, but since we have these 2 polynomials, we have no common factor. We can homogenize them, adding this third coordinate, and go to P2 of C. And since any holomorphic endomorphism of P2 can be written like 3 homogeneous polynomial, which have no common factors. Otherwise, you have some indeterminacy set, and that's not good. Well, this is what we have to search for. We have to search for something which is a map going to P2. Okay, so I hope I answered a little, I made it a little more clear why I'm so interested in finding a wandering domain for a polynomial map in C2. And I'm not asking for, well, more exotic maps. So in here, well, I think maybe it's better to do it like this. So I know, well, do you mind if we go to higher dimension straight away like this? As you see, I'm not doing it in a very weird way. I'm just being one-dimensional in here, and I will add something more in here, and you will see it's not so two-dimensional. You can see it like C1.5, even if the real problem is that I cannot draw anything, but I will try anyways. Okay, so the idea of Lubitsch was, let's use Skew products, okay, and see what happens. Well, if you use a Skew product, so like this, what's happening, so let me be technologic and be, no, am I, yes. Okay, so I didn't have to write it down again. So in here, what's happening is that if you take G of W, which is your one-dimensional polynomial, then you can ask yourself, okay, what happens to its Fatou component? So the Fatou component that it can have, it's not anything. It can have a super attracting component, an attracting one, a parabolic one, or a rotation one. And in this case, I will only have Siegel disks. In all these cases, so, well, these two always go together, but for this specification, it's better to separate them. In all these cases, I have a fixed point. So since I have a fixed point, let me change coordinates so that my fixed point is at the origin. So assume, without loss of generality, that, well, 0 is fixed by G. Okay, so 0 is fixed. And why am I, so this is something that it's in my mind, but I didn't say it, so I should. So why am I considering Fatou components for G? Well, if I have a Fatou component for capital F here, well, of course, it has to project. So when I project it down on the W coordinate, I will have a holomorphic map, an holomorphic endomorphism of C, well, actually a polynomial function in C, and it has to have a Fatou component, okay? Because whenever I am, here I have C2, I have my map F, and I have my Fatou component of capital F, everything is called F. When you go down to C and you consider the action of G, well, this has to project to a Fatou component of little g, because, well, when you iterate here, you're considering normality for this kind of iterates, and it's just one-dimensional iterates. And so if I'm searching for a domain which is wandering, then it will project to a Fatou component of little g, and little g is one-dimensional, so I know how to classify them. So the idea is, now we consider g, we take a fixed point, because in all these components, they have a fixed point. I will study this fixed point, and I will see whether or not I'm able to build a wandering Fatou component for the big capital F. Okay?
Sorry.
Yes.
Sorry, okay, so you have then this projection from the big Fatou component of F and the Fatou component of G. Do you know How are the fibers of this projection?
Oh, it's just the projection on the second coordinate.
Yes, but did you take the p minus 1 at some point in the Fatou component and look what is the pre-image of this? It's maybe very complicated, I suppose.
Yeah, this will be very complicated. Actually, it's very difficult to, sorry, I have some working going on in the math departments. So this will be very complicated, but if you prefer not to see it with, how to say it?
I am very happy with this, just a question.
Oh, yeah. No, actually, so there is a computation way of seeing it's just I iterate f and I have to iterate g. And so if f is normal, then g is normal as well. Okay, gn is normal as well. So taking the projection back, it's very complicated and you don't know. I mean, it might be that you have a product of some, I'm sorry. Yeah. So you can't see it exactly precisely. It could be that when you go upstairs, you have several Fatou components just projecting to the same one. So you don't know. Okay, so this is not what I'm going to do. I'm going to study what's happened to fibers. So in here, when I have a skew product, what's happening in here is that, so let me take, so this is C in here, and this is the W coordinate. So I have a fixed point in here, 0, and I'm asking, okay, if I'm in a super attracting component, this means that, well, if I take fibers, W equal to W naught, well, each fiber will be sent by G into another fiber, so which is going to be equal to G of W naught. And so if I'm in this attracting case, well, these orbits are going to accumulate on both sides. Okay, so I have these fibers and I have a special one. The special fiber that I have is W equal to 0, because if I consider f of z 0, then it's simply going to be f of z 0, which is one-dimensional. Well, sorry, g of 0, but g of 0 is 0, okay? And now I have, as I said, I have this special one, so let me erase all of this. Well, that's good. Let me erase I have this special fiber, okay, and I can ask, okay, in here I have a one-dimensional, so let me call this f naught. In here I have a one-dimensional action again of a polynomial in C, so this is W equal to 0. So, and in here what I also have Fatou components, which can be super attracting basin, well, attracting basin, parabolic basins, or Siegel disks. And so in here, you can ask, this is a really good question, is like, you have a Fatou component for F naught, is it true that it's somehow the image or the intersection of my invariant fiber with a bigger Fatou component, which is like in the product case? Okay, or so if this is true, well, whenever you have if this is true for all of these components, which is something which happens in some of these cases, then of course on the same component downstairs, you will be, I mean, when you take the pre-image, then you are intersecting several different Fatou components for the capital F stuff. So this is not what we are going to do here today and tomorrow, if everything goes well. So what I'm simply saying is that if I have a Fatou component somewhere, then it has to project downward. And I will not take the pre-image of capital omega of little g, because exactly I could go in several different Fatou components. Does it answer your question?
Yes, you explained perfectly. Thank you.
Okay, thank you. So, yeah, so actually your question was very good because it led me to where I wanted to go. So in here, you can ask yourself, okay, well, the easiest case should be the attracting case. You can ask yourself, okay, is it true that all my photo components in this case, or for this, F naught, which is the one-dimensional map, are bulging, or inflating, like you can see them like the intersection. So this is really not three-dimensional, but I hope it speaks to you as it speaks to me. So is it coming from a two-dimensional one or not? And so this is a question, but this is not a question related to wandering domains. And you can ask, can I have a wandering domain coming nearby this invariant fiber? So it turns out, so the story is long, let me make it short. It turns out whenever you have a super attracting fiber in here, then this is not happening. You can't have a wandering photo component coming nearby this invariant fiber, because otherwise it would not have enough space. And so, well, actually, this is also true when you are in the attracting case, meaning that the multiplier at 0 for G, so the first derivative of G at 0 is in modulus less than 1, but different from 0. Well, I'm cheating a little because you have to add some conditions, but this is not true also. So what Lubitsch, proposed was, let's use parabolic points for G. So when I use a parabolic point for G, then I will get attraction only on one side. I will forget about trying to have to see whether they are bulging or not, my photo components for F naught. But you can ask yourself, okay, look, so I'm starting at W naught, and I will go to, I will go towards 0, so towards the invariant fiber, but not too fast. So Wn is like 1/n. Remember from what we said yesterday. Okay? And now you can say, oh, look, maybe, if my map in here is not too complicated, so let's say that f of zw, sorry, I don't know why it's doing that, is equal to, f of z plus a little perturbation, so plus alpha w. So I'm just perturbating a little a one-dimensional map. So maybe I'm able to study the dynamics of this kind of map. So in here I have, so I took g of w, which was, say, w minus w squared. Okay, maybe you wanted the polynomial maybe of higher degree. Let's say big of w cubed, and we'll see what happens. So maybe if I start from here and I perturb my one-dimensional map with this alpha w, I will be able to say something, to build a wandering component. And the idea underlining, so the fact that it is inside and you don't see yet, is that, I could start by z plus z squared. I will need I order, so let me put a big O of z cubed, because I need it, plus alpha w. And so in here, if I do that, this reminds people, and now reminds also me, of parabolic implosion. So I'm perturbating a parabolic map, so what we studied yesterday, with something in here which is like 1/n. And so I can ask, okay, does dynamics from one variable, so what we call parabolic implosion, help me to prove or not that there is a wandering photo component which is coming nearby this invariant fiber, but taking longer and longer to go there, and so never getting back to itself. So this is the idea underlining. So this, let me write the magic word parabolic implosion. And I think maybe it is time that I write a proper statement somewhere. So let me state it here, and then I will go back to where I wanted to start today. Okay, so this is a theorem, and it's a bunch of people. So Astor, Buff, Jardin, Peters, myself, and I think it appeared in 2016. So let me write it like this. So the polynomial Skew product f zw equals to z plus z squared plus az cubed plus pi over 4 pi squared, sorry, over 4 w minus w squared. And now I have, since I want them to have the same degree, let me add whatever 1,000, 1 over 100, as you wish. Let's put 42. Like w cubed, okay, as a wandering factor component, if a is less than 1 and near enough to 1. So just to give you an idea, I mean, this is not proven, but somehow it's proven by computer. So when you do your computation somehow, it seems that a equal to 0.95 seems to work. I mean, the proof is simply saying if a is smaller than 1 real and near enough to 1, then we have 1. But, well, you know, now you can always try to do computation with computers, and it seems that this is fine. Okay, and
sorry, but sorry, this number a is completely independent of the coefficient of the omega-3, W3?
Yes, that's a very good point. And actually, so in here, I don't care at all of this. So if I wanted to put a map in here, but you have a family of maps, you can put in here whatever you want as soon as in here is just so. Let me put it in gray so it's not so visible, but you can add in the first coordinate any big O of Z4, and in the second coordinate a big O of W4. You can do it, and this will not change a single thing. And actually this A, we need it only for something which is related to the Fatou coordinates of this map.
Sorry, then with the terminology that I am used, that means that if you perturb the F in the category of the Skew product, you are getting an open set. It's not the same.
I don't think it's the same, because when you perturb it in the family of
only on the C4. Okay.
Yeah.
Thank you. No, I am completely wrong. Sorry.
No, I mean, it's like it's a natural question. I also put it in gray, so it's not really seeable. Maybe I should have put it in another color, but I want you to forget about it. Actually, you can also forget about this. We don't need it. The only thing we need to know is that in here we have a parabolic map, and that Wn behaves like 1 over n. And so whenever I'm in here, I'm perturbating my map, like adding pi squared over 4, 1 over n. So now I don't want that, because this is not going to help me. I will iterate g n squared times. And if I iterate g n squared time, Wn is going to behave like 1 over n squared. And in here, I will be happy because this will be like pi over 2n, all of it squared. Okay, so the tool that we're going to use, well, we used actually was Parabolic Implosion. And so let me go back to the first page that I didn't show because I started a little downer. So this was a recap from what we did yesterday. So yesterday we said, oh, look, if I have a map of this form of polynomial, because I want to stay in this class, but actually this is true more in general, but I want to have something which is defined all over C. So I take a polynomial. What's happening is that I have a small attracting pedal, a small repelling pedal. I can construct a global basin. People in holomorphic dynamics who know that this should be a cauliflower will be nice to me. I'm really nuts in drawing. So this is my cauliflower more or less, okay? And so in this in this light green region, this is just a recap. You saw it yesterday. So we have this attracting for two coordinates, and we also know how to write it asymptotically when we are going to infinity in the right half plane. And we also have this, so in here we had the repelling for two coordinate, meaning the attracting for two coordinate for F inverse. And so taking a local inverse, well, I didn't prove it. Well, I didn't prove anything, but just to give you the statement, you can find a repelling for two parameterization, which is defined all over C. This is important. And it's semi-conjugating the translation by one to the action of F. Okay, and again, I can write it's a asymptotics as the real part of U is going, so now it's going to the other side, so backward to minus infinity. And so you see, these are coordinates. I mean, they're nothing to do with dynamics. They're just semi-conjugating F and the translation by one. But, well, if you look at them, they shouldn't tell you anything more about the dynamics. And the fun fact is that indeed they do. And they are exactly what are entering in this thing that we called parabolic implosion. So let me go to a new page and let me explain what I mean. So in here you saw that I am having this dynamics and I am perturbating it by adding a perturbation on W, and W is moving as well. So at each step, when you iterate, well, you're going to change the W in here. So the first question is, okay, but what happens if I don't change it? So let's see if I perturbate. Let me see where I am. Yes. Let me consider F lambda of Z, which is equal to Z plus Z squared. I'm not putting the rest. I don't care for the moment. Plus lambda, and lambda is a real number. Okay, it's a real parameter. So if lambda is 0, this is what I always tell to my students, start for the easy case. If lambda is 0, then we already did everything. So F0 of Z is simply Z plus Z squared. We have a fixed point in the origin. We have the loop of Pythagoras theorem. We know everything we wanted to know. If lambda is non-zero, then we don't have 0 as a fixed point anymore because the image of 0 is lambda. But what we have is that we have two fixed points. So, the origin went to two fixed points. And I can also compute them because it is easy. So these are equal to the square root, plus or minus the square root of minus lambda. And the multiplier, well, I simply have to derive this. So this is a parameter, so it disappears, and put the point inside. So the multipliers are F prime, Z plus lambda, and C plus minus, and it's simply 1 plus or minus 2 square root of minus lambda. Okay, so I have two cases. Well, either this root is real or not. So, well, case 1, I have lambda is equal to minus epsilon square because I don't like to use square roots with epsilon a real positive number. And in this case, what's happening is that, so z plus and minus or plus and minus epsilon. So I went to this situation where I'm trying to be consistent with my notation of colors, where I had and that's with drawing. So this was my attracting part and this was my repelling part. And this was attracting. And now essentially, so if you look at me, what I'm going to do is, well, I'm switching my fixed point into 2 fixed points horizontally. And so what's happening is that I still have a green region. Let's close it. And I will still have a repelling region because, so I have my 2 fixed points. So this is minus epsilon and this is plus epsilon, if I'm not mistaken, because when I compute f prime lambda at minus epsilon, this is simply 1 minus 2 epsilon, which is less than 1, and f prime lambda at plus epsilon, this is 1 plus 2 epsilon, which is bigger than 1. Okay, so in here, I have a repelling fixed point, and in here I have something which is attractive. All right, so, well, this doesn't give me much information. So the dynamics is this. I don't have to take attracting for 2 coordinates or repelling for 2 coordinates to describe this. So let's see what happens in the second case. So in case 2, okay, sorry, I have somebody who entered in my door and now is going away. Cool. This is the the nice thing of the direct, right? Sorry about that. So case 2 is the following. Well, we had 3 cases, right? Lambda is equal to 0. Lambda is minus a square of a positive real number. So I'm left to see what happens if lambda is epsilon squared, again with epsilon positive and real. All right? So, okay, I'm not going to do this again. Let me put it here. Okay, so this time my 2 points have moved, but in the vertical line. So they are plus and minus I epsilon, and this changes everything because now f lambda at plus and minus I epsilon, it's simply 1 plus and minus 2I epsilon. And whatever you do, this complex number will have modulus bigger than 1. Okay? So modulus of, this is a prime, sorry. F lambda prime plus and minus 1 I epsilon is bigger than 1. It's not so bigger than 1. It's just if epsilon is very small, what's happening is that it's slightly repelling. It's just sending people away, but not in a bad way. So what happened in here is that my 2 points came to I epsilon and minus I epsilon. And I'm doing it small because I'm thinking about it as being small, but let's put it big so that you can see something. Well, this is my big, okay? And in here, what you can imagine and what is going to happen is that these 2 regions, they were touching at the fixed point, the origin. So they are going to open. And so in here, what one can prove, what Laverse proved actually, is the following. So let's see. Okay. Yeah. It's really annoying. Anyways, so what's going to happen is the following. Whenever I'm far away from the origin, iterating f lambda or iterating f naught doesn't change much. Because if z is big compared to epsilon, well, epsilon doesn't really care. I mean, the epsilon, the contribution of epsilon squared is not changing at all. But what happens when I'm starting to enter into this region? Well, this was my attracting region, all right? So if I enter from here for F naught, so let me put names, I didn't say it. So this was the situation for F naught of Z, which is Z plus Z squared. And this is F epsilon squared of Z, which is Z plus Z squared plus epsilon squared. So in here, I will never be able to cross from the attracting part to the repelling part. But what happens in here? Well, I start iterating my map. I went inside, I iterate, and nobody can stop me in here. And moreover, what's going to happen is that I have somebody here pushing me away and somebody here pushing me away at the same rate. And so it's going to happen like being in an egg beater. So I have something pushing from one side, something pushing from the other side. I'm staying in the middle, I'm floating in the middle, and I'm passing through this corridor, which is now open, to go to this repelling part. And once I'm here, well, I can continue. I continue, and then once I'm out, I can compare the dynamics of epsilon squared. Sorry, I can approach it by simply using F naught, and I'm happy. So in here, what's really happening is this. So I think this terminology goes back to Dwadi, who talked about egg beaters. And it's really, I mean, when you see it the first time, you say, oh yeah, sure, it has to be that, right? So I see my egg beaters in here, but they're not exactly, well, they are also actually moving in circles like that because there is this rotation part, but well, they are pushing this little point away, and this little point can continue to pass through. And so this is usually called the egg beater. And now what Laverse proved, I will not prove it to you. Well, of course, not today. So I will finish in 2 minutes. I will simply give the theorem of Laverse in here is the following. So you can actually, what happens is that to describe what's happening to this kind of iterates of well, this is, sorry, not the iteration not of F naught of epsilon squared, you can use your attracting and repelling, well, attracting for two coordinate and repelling for two parameterization for F naught. Okay, so this is the result that it proved. So actually an easier version of this result. So, and this was, I noted down, so 1989. Well, so again, F is my polynomial of the form F of Z is Z plus Z squared plus ego of Z cubed. And you take Mn. So Mn is going to be the number of iterations that you're going to have. So this is a natural sequence tending to infinity. And epsilon n, so this is going to be my epsilons in here. And I want epsilon n such that it's behaving like pi over Mn. Then F plus epsilon n squared iterated Mn times converges to what we call the Laverse map, which is simply I'm taking the repelling Fatou parameterization of F naught. Let me put F naught in here. Composed with the attracting Fatou coordinate locally uniformly on the basin, the attracting parabolic basin of F naught. And actually, so let's make it easier, even easier. So I hope you don't mind if I erase it. in here, let me make an user statement. If epsilon n behaves like pi over 2n, then in here, I simply iterated 2n times, and I will land to this Laverse map. And actually, this is what more or less what we needed, because now you have a map which is one-dimensional, and you can ask yourself, does it have a, for example, an attracting point? And actually, this is not proven by Laverse, but this is more or less, I will finish in 1 minute, I promise. This is more or less, well, this is something that we can prove, and this is a computation, so a proposition. If a is less than 1 and a smaller, well, close enough to 1, then, so a in here, sorry, I knew that I had to write it down differently. Then the Laverse map of F naught, so of this map, as an attracting fixed point. Psi inside the parabolic basin of F naught. And so, well, we'll see tomorrow that we don't have this result because we're not, so our epsilon n now for us, it is Wn. So it's changing at every step of the way. But we could, so there is a clear proposition that we proved showing that, well, you know, it's not 2n times that we have to iterate. We will iterate a little more, and that will be it. And the existence of an attracting fixed point for the Laverse map will give us the existence of a component, which is wandering around nearby this invariant fiber. And I will stop it here because you have a long day ahead, and I had a long day before. Thank you very much.
Thank you much. I don't know if we have some questions or comments. Well, if there are no more questions.
Lorenzo, may I ask?
Yes, please, Ali.
Maybe not very related, Jasmin, to exactly to your talk, but somehow related. It's a real question in nature. So is there anything different when you go to higher dimensional complex dynamics? So, I mean, if you want, I see you have many problems in C2, PC2, but is there any difference in nature in higher dimension complex dynamics with 2 dimension?
So when I to higher than 2 or just a
I mean C3, PC3 or PCN. So you may ask all of this question. I am just very naively asking you a question because of the difference in surface dynamics, 2 dimension and higher dimension in real dynamics. So it is really a very naive question. What happens in complex dynamics? Is it so complex that you don't go, or it is similar?
So in maybe in 2 words, I would say, but that's really a, so okay, computation gets more difficult. If you want to compute and you want to see what happens locally, then it's a mess, and then you have the more space you have, the worse is somehow. But actually, the heuristics, at least from my point of view, which is a very personal one, is once you understand how it works in C2 and C1, dimension 2 and dimension 3, then you are more or less the idea of when it happens in higher dimension. The big step is to understand things in dimension 2, and I'm adding dimension 3 because in dimension 2, there is a lot of space, but not quite. Sometimes you have more space. Well, you need more space to see worst things happening. Just to be here, and I will stop there because I understand we are almost out of time, and you need to have at least 5 minutes break. But for example, you would expect that the linear part tells you everything you want to know. right? So if you have two eigenvalues, so now you're in dimension 2. If you have two eigenvalues which are elliptic, so rotation, irrational rotations, then you say, okay, I would expect to have no orbit involving the origin, except for the origin, which is what happens in dimension 1. And actually, you can prove that it is not true. You can prove that, well, in most cases, maybe it is true, but if your two eigenvalues have resonances of relations in between, well, you can have somehow parabolic dynamics. And this is, well, this is something big. I mean, because whenever, this is telling to you that the dynamics is richer. But I think
thank you.
My answer here.
Thank you.
I think that it's time to thank again Jasmin for a very nice talk.
Yeah.